The 2019 flash drought was remarkable. We started the year extremely wet, potentially a record-breaking year, and then Mother Nature turned off the faucet and turned on the oven. September was the driest on record and the second warmest on record.
This remarkable flash drought impacted much of the southeastern United States, hitting Kentucky especially hard. At the beginning of September, 0% of the state was in drought, and by the end of the month, drought coverage was up to over 90%. This is not the first time the area has experienced a phenomenon like this. In 2012, there was a flash drought that developed over just 2 months during the growing season and resulted in over $30 billion in losses to the agricultural sector. So what is flash drought? Flash drought is a type of agricultural drought that develops very rapidly over the course of a few weeks. The key to flash drought is that precipitation deficits are coupled with persistent atmospheric anomalies, such as higher temperatures, stronger winds, or more sun. These persistent atmospheric anomalies drive an increase in evaporative demand. Think of evaporative demand as the thirst the atmosphere has for moisture. This increased thirst in the environment leads to the depletion of soil moisture and eventually vegetation stress that make it an agricultural drought and of special concern to the Ohio River Valley. Situated south of the Great Lakes and west of the Appalachian Mountains, the Ohio River Valley is a major agricultural producer, with almost 50 million acres and farms across the watershed. The 2017 Census of Agriculture reported that the annual market value of agricultural products in Kentucky alone was over $5 billion. The basin also provides freshwater resources for a variety of sectors, including manufacturing, energy, and recreation, along with agriculture. Flash drought can lead to decreased yield, damaging crops and pastures. It can also lead to an increase in wildfire risk and the occurrence of harmful algal blooms. The patterns of excess moisture followed by drought the area has seen are expected to continue and intensify. This adds to the concerns of forecasters as they want more tools to help identify the flash drought onset and provide early warnings to stakeholders.
Flash drought detection and warning in Kentucky is really challenging and because of a couple opposing reasons. First of all, given that it is a water-rich environment, typically when it starts to get dry, it rains. And so if we pull the trigger too soon in terms of early warning, it's often for naught. On the other hand, when a dry spell extends, as moisture is extracted out of the environment, temperatures can increase and we can see heat waves develop that further accentuate the rate of drought development. So those opposing factors make drought early warning particularly challenging in our region.
To help address these challenges, the NASA-developed team at the National Centers for Environmental Information in North Carolina partnered with the Kentucky Climate Center and NOAA's National Weather Service Ohio River Forecasting Center. They analyzed and compared satellite-derived drought indices and gauge-based environmental data to better understand flash drought dynamics and guide early forecasting efforts, using the September 2019 events as a case study. Drought indices are commonly used to forecast drought. They quantitatively categorize drought by combining data from one or more indicators, such as precipitation or evapotranspiration, which is water loss from both the land and plants. The Standardized Precipitation Index, or SPI, is widely used operationally for drought forecasting and management. However, it solely considers precipitation as a drought indicator. Currently, project partners do not use drought indices sensitive to flash drought in forecasting models. Considering the key factors that drive flash drought mentioned before and its rapid onset, the team looked into 3 other drought indicators that include different environmental drivers to aid forecasters. One of these is SPEI, or the Standardized Precipitation Evapotranspiration Index. Similar to SPI, SPEI includes evapotranspiration along with precipitation to look at the climatic water balance in the environment. LARI, or the Landscape Evaporative Response Index, inputs land surface temperatures from NASA's Terra Modis satellite and reference evapotranspiration to model anomalies in actual evapotranspiration, essentially a reflection of land surface moisture available for plants in the atmosphere. EDDI, or the Evaporative Demand Drought Index, considers temperature, wind speed, humidity, and solar radiation, along with reference evapotranspiration, to model anomalies in evaporative demand, that thirst the atmosphere has for water. The developed team downloaded the data, processed it to be a uniform resolution, and reclassified it to the U.S. Drought Monitor categories. An interactive ArcGIS Pro document was created for forecasters to assess and compare spatial and temporal patterns of the different drought index products. Time series of the percent area of drought categories and subwatersheds were also produced from 2010 to 2019 in order to further analyze the behavior of the indices at different events. Eddy exhibited more sensitivity, likely due to the meteorological variation of its inputs, but project partners identified it as a leading indicator and will now use it to raise their awareness of when to start paying closer attention to potential for flash drought. The Kentucky Climate Center houses the Kentucky Mesonet, a system of stations that collect climate and weather data across the state used for forecasting. Focusing on soil moisture, the team compared ground measurements by the Mesonet to satellite-derived data from NASA's Soil Moisture Active Passive Satellite, or SMAP. SMAP collects data across the globe to estimate surface soil moisture measurements.
There's a natural fit between the Kentucky Mesonet and NASA remote sensing data. The Mesonet provides us point observations where we have our stations located, while that remote sensing data helps to fill in the mosaic and add more context and detail to what's happening in Kentucky. That's particularly valuable to us.
The analysis showed that SMAP and Mesonet measurement values differed, but displayed similar patterns of wetness and dryness. The team used these comparisons to help the Kentucky Climate Center identify which stations had better patterns of agreement.
I think the biggest value of this work is going to be increased confidence. That is, we'll have a better picture and more reliable information. This increased confidence will help us to be more proactive in terms of addressing issues.